Good morning. Hello. Good morning.
Good morning, sir.
Good morning.
Good morning, sir. Good morning. Good morning. Fine. So as I told you people yesterday, this among the two methods which we are seeing, working stress method, just the basics alone will be there for you. Okay. So according to that, some two problems we have solved yesterday. So only those kind of problems will come. Because you're not going to deal with design in working stress method because it is not the main part of your reinforced concrete design according to IS 456. The main part of design according to IS 456 for reinforced concrete will be your limit state method. So that is what we will be covering in detail for this entire course. So the basics of this limit state method we have already seen 2 classes before. So where you saw that basically limit state method is based on probabilities. Okay. So what is the probability of the loads exceeding the resistances? So based on that, depending on the uncertainties, you make so you see the you see where you make sure that for the most probable cases your resistances will be more than your load effects. And based on that, you also define 2 limit states. One is something which is actually going to make your structure collapse. Other thing is the one which will make just other hindrances to your structure, like excessive deflection or vibration. Durability. Durability means like your durability things like water leaking and some patches forming on the structure, etc. Okay, so those kind of things are limit states of serviceability. So these things you saw till last week. So going into it, the first question is, so as you know, there are several types of loads which can act on a structure. Okay, for example, you can for example look over here and see that you have something known as permanent loads and imposed loads or dead and live loads. So in this picture, it is also shown to you what is the meaning of dead loads. So for example, things which are always going to be there. For example, the weight of the wall, the weight of the floor itself, the weight of the beams, the weight of the columns. So whether you build a beam or a column or slab, any structure you build, it is going to have its own weight, and it should be capable of withstanding its own weight itself. Okay, so those things are known as dead loads. There are other things known as live loads or imposed loads, which mean things which are going to act on the structure because of its usage. Okay, so for example, if it's a normal building, you have humans, you have furnitures. If you have something like shopping malls or things like that, then you have the racks as well. You have the showpiece items. And then if it's a car park, you have the weight of the cars being parked. Okay, so those things which depend on the usage and can be moved. Those things are live loads. Now, this permanent load and live loads, which direction do they act? Dead load, which direction does it act? In general, the weight of a structure or things which are based on weight. In which direction does the load act?
Negative Y, sir.
Negative?
Y. Y-axis, negative
Okay, in
Y-axis.
terms of Cartesian, right? But can you say it in without referring to any axis? Can you tell which direction?
So the direction of gravity.
Direction of gravity. Okay. So basically, dead and live loads mostly they will act on the direction of gravity. Okay, and for most common structures like 1 or 2 story buildings, taking care of permanent, and that too in normal places like things buildings which are not on mountains or which are not on coastal areas, things like that. A normal structure, as long as most of the people, they will just consider the dead loads and live loads alone, and they will go ahead and design it. But that's not the only load. You can very tall buildings. You also have the issue of wind. So if you have 10, say 5-6 story buildings, then you cannot just make your design based on the dead and live loads. Wind also causes a heavy load. Okay, wind is not a joke. Wind can actually generate quite a lot of force. Wind can actually move structures. Okay, olden days wind used to move ships. Okay, how did Vasco da Gama find India? Okay, they didn't have motor-raised boats and all. It's all based on sail and winds. So many kilometers. No, pushing big ships. That's what wind is capable of. So therefore, even on buildings, the load which can be caused by wind can be quite high. Only thing is, these things are usually, they are not a constant value. They keep varying depending on season, depending on hourly basis, depending on interval basis itself. The velocity of wind and therefore the pressure of wind will actually keep varying. So that is one thing. So if wind is blowing in a certain direction, the direction which it impacts, you will have a positive pressure, and when the wind actually it crosses the obstruction and goes to the other side, you will have a negative pressure on that side, or it's known as suction. So those people who took applied hydraulic engineering last semester, so you people I think would be aware how there's a pressure or suction created. Okay, so it's all based on this theory of drag and those things you will be aware of. So these are the things which are related to wind. Of course, then yesterday there was a news that there was a earthquake somewhere in Tamil Nadu. Did people actually read about it? Small minor earthquake, minor tremor. People heard of it on
Chennai in the Bay of Bengal.
Yeah, about 300 kilometers away from, I think, Rajamundry or somewhere in the Bay of Bengal, there was the epicenter, and not a very big earthquake. At the location it was about 5 on Richter scale, but anyway, what was felt in Chennai was not much. But still, that is one thing. It can cause. So you people know that heavy earthquakes, buildings fall. So why do they fall? Because earthquake usually acts from the bottom. It does something known as it kind of shakes the base of the building, and because the base of the building is shaken, this building which is at rest, it starts moving with an acceleration, and when an object at rest is subjected to a sudden acceleration, what kind of force is generated?
Inertial force.
Inertial force. So usually there will be inertial forces developed in the structure, which are also forces, and they are actually caused by this seismic effect. So especially for heavy structures, tall structures, no, because the weight is more, inertial force will be more. So that's why as you keep going up, at the bottom the acceleration will be less, but as you keep going up, the acceleration is actually more when the building shakes. So the initial forces will also actually increase as you go up. So these are all different forces. Now one thing is, as far as permanent and live loads are concerned, so among these things, permanent load, live load, wind load, and seismic load, which is the one that you can predict with most certainty, and which is the one you can predict with least certainty?
The permanent and live we can find with most certainty, and seismic is with least.
Seismic is with least, and even wind also. Wind at least it's better. You have wind record data and you can predict. But yeah, like you said, that's the case, and therefore, because many of these loads you do not actually know you do not exactly know how it actually happens. You actually account for it by, everything is a probability, and you cannot predict with exact certainty. Because of that, you factor in that uncertainty and you give something known as a factor of safety. So, in general, any single load that you take, whether it is permanent, live, or wind or seismic, as long as you are going to consider only one single type of load, you factor that load by 1.5 when you make your design. Okay. For example, if you have dead load, and do I have the table? Okay, not there. So if you open your code book, you'll have a table which lists all the factors of safety. So maybe at the end of this class I'll show that table. So any load taken in isolation, you will adopt a factor of 1.5. If you combine gravity loads with lateral loads, gravity loads means these are gravity loads, these are lateral loads, wind and seismic. If you're going to take those loads in combination, you don't need to take 1.5. You can reduce your factor and take a factor of 1.2. Meaning that, for example, the load is 3 kilonewton per meter square. Okay, if that is the load, if you're taking only one single load, say that is the dead load, then for design you have to consider 3 into 1.5, 4.5 kilonewton per meter square. However, if you're going to take dead load and wind load together, the dead load is 3, say wind load is 1, 3 and 1. So in such a case, you will say 3 plus 1, both of them together, times, instead of 1.5, you say times 1.2. So 4 into 1.2, 4.8 kilonewton per meter square. So like that, depending on whether you take loads in isolation or whether you're going to combine a gravity load with the lateral load, you will reduce the factor of safety and say, let me not take a big factor of safety, let me take a much smaller factor of safety. So there is a reason for this. So now, so you take only one load, you take 1.5 as the factor, you take them in combination, you take 1.2. There's a very simple reason for this. Can anyone guess why when you take more loads together, you reduce the factor of safety? By the way, this is all for design purpose. So when you design for loads in combination, you reduce the factor of safety to be considered. Any reason why?
So when we are increasing the load, we are accounting for some uncertainty. So we are
You're
just
about
reducing. Sir, like we are designing for a greater load than expected.
okay.
So as we are designing for a larger load, so we are reducing the factor of safety. Like already we are taking a larger load.
Okay. Okay, that is one reason. One reason is no, you don't want to become too ridiculously. It becomes too uneconomical to keep factoring everything by 1.5 together. So that is one reason. There's a more rational reason. Okay, by the way, the clue for that is whenever you design for wind, it is designed based on the recorded, based on the recorded peak wind loads you design. Similarly for seismic also, based on whatever is available on record. So based on that, you adopt a historically peak value, and based on that you design it. Okay, so that is the clue. So why when you take gravity in combination with that? By the way, the reason for taking 1.5 for gravity loads is the reason is, say for some reason there is an accidental loading which increases the dead load or a live load. You don't want to be caught unaware. That's why it's been raised by 1.5. Anything which is in isolation. Now the reason why you take 1.2 is they say, see this gravity load 1.5 factor is given so that in the unprecedented event that there's an overloading, you don't want to be unsafe. Similarly, if you take only wind separately, in the case that there is an unhistorically big storm which is happening and you don't want to be caught unaware there either. So why they reduce it to 1.2 when you combine both of them is there is a very small probability that at the same time the gravity load also becomes overloaded because of some reason, and at the same time there's a very big storm or a very big earthquake, both happening at the same instant of time. Okay, so it is very, very unlikely that both of those bad events happen together. Okay, only in a very historically unlucky situation that will happen, but it is not very sensible to consider such a situation for design purpose. Okay, so that is the reason that for most buildings they reduce this factor to 1.2, saying that it is very unlikely that both of these bad cases are going to happen at the same time. Okay, so that is the reason why it is reduced. Okay, then this is for limit states of collapse. So if you, for example, if you want to check whether a structure is going to fail under flexure or compression or torsion, so anything based on those reasons, if you're investigating or designing, you use these factors. If you're going to design something against serviceability, for example, you want to check whether a beam is not deflecting too much if it is within its deflection limit. So for such cases, you do not factor the loads, you just use one as the factor. Okay. Then of course, in the material, so one part is the load, other part is the resistance, which is the how much can the material resist. For example, concrete, M25 concrete. Okay, you want the compressive strength to be 25. Okay, but you use a factor of safety for the concrete, saying that even though you have an M25 concrete, you are going to factor it by 25. So you say that the design strength that you adopt for concrete will be 25 divided by 1.5. Okay, so this is another difference you should remember. When you factor loads, the factor is multiplied. When you factor the resistance, the factor is divided. Okay, so that is one thing you have to remember. Similarly, for steel, which is produced at the factory, you do not divide the, for example, if it is Fe 500 yield strength, instead of using 1.5, you just use 1.15 as the factor. So 500 divided by 1.15. So there is, here you use 1.5 as the factor for material resistance. For steel, you use 1.15, a lower factor for the material resistance. Why this difference? Why for?
In factory, we'll have quality assurance team.
In which one?
In factory, we'll have all conditions where all the conditions will be met.
Yeah.
There will be quality control team, so it will be all will be in a correct manner.
Yeah, basically it's for quality control. In fact, these days even concrete, when they are making it in the factory and automated process they are having for big projects and all, there and all, even for concrete it is not necessary to use 1.5, but in the code book it is specified as 1.5, so everybody uses 1.5. So anyway, concrete, the material itself is a bit uncertain as compared to steel, which is homogeneous, which is actually homogeneous. Concrete is not actually homogeneous, it is just assumed as homogeneous for design, I mean for its analysis, that's it. So this is the reason why, so you have material factor of safety and you also have a factor of safety for the load. In limit state method, this is the basis, you have to take care of it. So you see here that for load, separately you have a factor of safety. For material, you separately have a factor of safety. In working stress method, do you remember what you did? Do you remember if there was a was there a factor of safety for load, or was there a factor of safety for material resistance? For which was there a factor of safety in working stress method?
For the material used.
What was the factor of safety? For concrete, what was
1 by 3.
Yeah, about 1 by 3. Okay, so basically, no, they have set a permissible limit. Sigma CBC means permissible compressive stress in concrete and bending. Okay, so they set a permissible limit that basically functions as a factor. Okay, so in working stress method, that is where you make the factor of safety. Some people use even load factor of safety also in working stress method, but it is not specified like that in the code book. But however, when you come to limit state method, you say that you are not going to use any permissible limits. Okay, you are going to just use whatever is the FCK or FY, but separately you will apply a material factor of safety. Separately you apply a factor of safety for the load. So how do you do it for the material? This is how it is done. So for concrete, if you take, so this is say FCK. This is the strain curve. This is your grade of concrete, so FCK. And so FCK divided by 1.5 will come to there's some mistake here, I suppose. Yeah, this is 0.67. Okay. You come to 0.67 FCK over here. Okay, so this is the reason why how you apply your material factor of safety. So this is, so why is 0.67 FCK? So the general norm is design strength equals 83% of the cylindrical. This is just a norm which is used. We use cube strength for our compressive strength test and all in the lab. Okay, but as told initially some few classes back, cylinder strength is actually more representative for concrete strength, and in general that will be the cube strength will usually be only 85% of cylindrical strength. Okay, sorry, will be 80% of the cylindrical. So you have the design norm, which is 85% of cylindrical strength, and then the cube strength, which is 80% of that cylindrical strength itself. Okay, so that multiplied together is 0.8 times 0.85, which is about 0.67. Okay, so it comes actually 0.68, but we use 0.67 because it is easy to remember as 2 by 3. So this 0.67 will further be divided by gamma m. Whenever you see the letter gamma, gamma means factor of safety. The symbol gamma is used to denote the factor of safety. M means subscript m means material. So gamma subscript m means material factor of safety. This is concrete. So you divide it by material factor of safety, which is how much is the material factor of safety for concrete seen in the previous slide?
1.5.
1.5. So 0.67 divided by 1.5. That is the actual design strength of concrete that you will use. So 0.67 divided by 1.5 will come 0.447. In our code book they say 0.446, but okay, it's just third significant digit is varying, that's okay. So this is how it comes from FCK. You apply, you say that only 85% of the cylindrical strength is usable, so it comes to 0.85 FCK. From 0.85 FCK you reduce it to another 0.80% because you say cube strength is only 80% of the cylindrical strength. So 0.85 times another 0.8, it comes down to 0.67, and divided by the material factor of safety, it comes down to this level. Okay, so this is how it is. So this is the stress strain curve of concrete. So basically it says the stress in concrete is 0.447 FCK times 2 into this. Have you seen this equation before? Except the 0.447. Have you seen the remaining of this equation somewhere before in previous classes? Anyone remembers?
Yes,
By
sir.
chance?
In working stress method, the stress versus strain curve.
This is the equation for the stress versus strain curve in the nonlinear part. Okay, so you just add that design factor, which is 0.447. It becomes the design stress strain curve. Okay, this is actual stress strain curve. This is a design stress strain curve. Okay, and that is given by this equation. Okay, so as long as the strain is less than 0.002, it is given by this equation. If it exceeds 0.002, then it becomes a flat line. So it is just given by 0.447 FCK. Okay, so this is design stress strain curve. So in the limit state method, you have similar assumptions as was there in the working stress method. So plane sections remain plane before and after bending, and as you know from the material properties of concrete, the concrete crushing strength in bending compression is 0.0035. Okay, the tensile strength of concrete as usual being ignored, and the stress in concrete follows the actual design stress strain curve, which means parabolic till strain 0.002, and after the strain crosses 0.002, it becomes a straight line, the stress. Okay, so what is the difference between limit state method and working stress method as far as this point is concerned? Do you remember the stress diagram for working stress method? What shape will it be?
Just a linear, sir.
Just a linear, meaning what's the shapes that's
Triangle.
Triangles. For basically because why was it only triangles there? I mean yeah, triangles mean it was linear. Okay, you took only the linear shape. Why was only a linear shape taken there in working stress method?
We took assumption that plane will be planes will be in plane, and plane surface will be plane surface only even before and after bending.
That's okay. That is yeah, that's correct. That is as far as the strain is concerned. So even here also that is even here also for the strain it is going to be that triangles only, because plane sections remain plane before and after bending. But as far as the stress is concerned, there we took stress also to be linear, triangle like this. Okay, that triangle. Here, why was it retained as a triangle? Why was it linear stress? Based on what assumption?
So because in 1/3 limit it will be always equal.
Meaning you limited the stress to the linear part itself.
Yes,
as far as the assumption is concerned in working stress method. Here you are not doing that. Instead, what was done is you took the actual shape and factored it. You took the actual stress curve and factored it by 0.447 or 0.446. So that's why the same shape is retained. So this is the stress block diagram of concrete in limit state method. Here the stress is 0.446 FCK. Then you have this parabolic curve, which is, so those who are confused how this shape comes, it is just this shape, this sustained curve. Just invert it up, you get the shape. Then of course in steel, you have a stress of maybe 0.87 Fy EST as the tensile force, or 0.87 Fy. Now, any idea where that 0.87 comes from for steel? 0.87 Fy. Any idea where the 0.87 comes
Modular
from?
ratio.
Not modular ratio.
for that
It will divided by 1.15.
Divided by 1.15, the factor. Okay, that's how that comes from. Okay, so then you have also this XU. This XU is nothing but your, in working stress method, what you found as X, or depth of the neutral axis. So here we call it as XU. Depth of the neutral axis is given as X subscript U, meaning depth of neutral axis of ultimate for getting the ultimate strength. What should be the XU? And XU max is nothing but similar to your KB. So do you remember yesterday in problem we had one K for balanced neutral axis, meaning that if you go below the balanced neutral axis, it is over-enforced. Go above the balanced neutral axis, it is tension failure, below is compression failure. So you remember that, right? So this XU max is similar to that KB, meaning that if the neutral axis depth goes below the XU max, or if XU exceeds XU max, it is over-reinforced. If XU is lesser than XU max, it is under-reinforced. So to find that XU max, you have this formula. So XU max divided by the depth, the effective depth D, is given by this formula. These numbers you should be able to remember because you know the meaning of all these numbers. You know what is 0.0035, you know what is 0.002, you know what is 0.87 Fy, you know what is CS, you know what all these things stand for. Okay, so you should be able to remember this. Okay, and so there you had a different formula, 280 by 280 plus 3 sigma st. Here also you can see it is dependent on the steel grade because Fy comes. So balanced neutral axis always, whether it is WSM, whether it is LSM, it will depend on what is the steel grade. Okay. Hello? I'm not able to hear. Huh? Hello, are you talking to me or somebody else? Okay. Okay, so there in working stress method, we had seen about compression failure and tension failure and balanced failure. So this is just a visual representation of that. So in limit state method, instead of just saying compression failure or tension failure, we use a slightly different term, which means almost the same thing. So we say whether the beam is under reinforced or over reinforced. Okay, so as I told you, if it is under reinforced, your steel is going to, under reinforced means which fails first? Steel or concrete?
Steel.
Steel used to elongate.
Steel will yield first. So whenever steel yields, it will actually elongate a lot. So because the steel is elongating, it will pull the concrete apart and you start having these cracks. So the cracks, the direction of the crack and the shape of the crack will tell you whether it is under reinforced or over reinforced. If your crack is like this, going from the bottom to the top of the beam, then that means it is happening because the steel is pulling apart the concrete because of elongation. Okay, that means it is under reinforced. Steel is yielding and elongating. So that's why it is creating vertical cracks like this in the concrete. If it is under reinforced, the crack will be different. You will hardly see any cracks coming from the bottom, and you see that concrete is crushing over here. Okay, you know that above the neutral axis it's compression. So above the neutral axis you see concrete crushes. So by looking at it, this is how you visually identify if the beam is failing through tension failure, under reinforced beam, or whether it is failing through compression failure, which means over reinforced. So this is how you visually identify them, and this is how the load deflection curves will look. So it is loaded here, deflection is measured over here using this dial gauge. So if you plot them, this is how it looks. An over reinforced beam, you see it will take quite a bit of load, and it fails all of a sudden. Then a balanced beam will take a good bit of load and it will elongate for quite a bit, and then it will fail. Under reinforced beam will may have a slightly lesser load carrying capacity, but it will elongate quite a lot, give you a lot of time to undertake repairs and corrective measures, and only if you keep ignoring it, it fails. And something which hardly has any reinforcement is just going to break like that, because you see that there's a very, very big difference between under reinforced beam and no reinforcement beam. Why is there such a big difference? This is only for
Property of concrete and steel are very,
yeah, it is because
like both properties of concrete and steel are different.
That is fine. Properties are different.
So concrete is weak in tension.
Concrete is weak in tension. So because when a beam is bending, there's one part compression, another part is tension. So when you do not have any reinforcement, what will happen to the tension part? So immediately when you load it, once the tension exceeds even if it is M25 concrete, if your tension exceeds 5 Newton per millimeter square stress, then itself concrete will fail. Okay, so that is the reason why there's such a big difference. So how do you do analysis by element state method? Okay, the first thing that you need to know is what type of section is it? Is it under reinforced? Is it balanced, or is it over reinforced? The way to find this is check the value of XU and compare it with XU max. Okay, so this XU max by D is constant for different grades of steel. So if you just go back here, XU max by D, this is a constant, this is a constant, this is a constant. ES is also usually a constant. Only Fy changes. So depending on what, so you just substitute the value of Fy over here, whether it is 415 or 500 or 550, 600, whatever it is, just substitute it, you will get a constant number. So that is what this constant numbers are: 0.53, 0.48, 0.46. And you note that as the grade of steel increases, this coefficient keeps reducing. So Fe500 is 0.46, Fe415 is 0.48, 0.53 for Fe250. These days you have till Fe600 itself, 600 or even more. So if you want to know what is this thing for those grades of steel, approximately you can find it by using the same formula, though it is not exactly accurate for grades higher than 500, because for grades greater than 500, the shape of the steel stress strain curve itself will have a slight variation. Okay, it will have very less linearity in it. So that formula cannot be used exactly, but okay, it will still give you a reasonably good value. And if you want to know this value for those grades of steel, go ahead and substitute 600 or 550 or whatever in that formula. You can get it. So this is the formula. Substitute the value of Fy, you can get. So then you will have to find out XU, the actual XU for your given beam. So like in working stress method, you found K, you compared it with KB. Okay, yesterday's problem. You found K. So how did you find K? What formula did you use? yesterday? Formula or the other method? What were the two methods to find K?
The one was using formula under root of 2 delta m plus delta m square minus delta m.
Okay. Other one? The other method was?
Other was finding the x and divided by depth.
Basically using the quadratic equation.
Yes.
Okay. So those two methods are there. So why I'm kind of reminding this is you found the actual neutral axis for the given beam section and compared it with KB. So you have to do the same thing here. You have to find out the actual where is the neutral axis for the beam and compare it with the maximum. Okay. So then you proceed to find out what is the total compressive force, and based on that you can find what is the ultimate moment of resistances. So there, to find the compressive force, what did you do in working stress method? After finding the K, what did you do to find the compressive force?
The area of triangle into sigma CBC.
Area of the triangle into sigma CBC. In that problem it was sigma CBC, but if it is not over-enforced, you will use FC. But whatever. So you took the area of that. So basically you did stress times area of that stress distribution diagram. So that's what you did. So you'll be doing the same thing here, except that now your stress block area is not a triangle. It's a parabola and a rectangle together. So basically, no, I have not shown the whole thing. But if you want, you can look at the book. You will know how this number comes. Okay, so basically, it is the area of this whole shape. Okay, the area of this whole shape. Here to here is XU. From this line to this dashed line, which is the neutral axis, this is XU. This is 0.446 FCK. So what you'll have to do is you'll have to take the centroid of this area and then this area. Okay, it's not centroid, sorry, you have to find this area, then you have to find the area of this parabola and then add both of them. Okay, so this is what you do. If you just do that, you will get this as your area. Then that times the breadth of the beam will give you total compressive force. 0.362 FCKB into XU equals the compressive force acting on that beam at that section. Okay. Now, in WSM we found the compressive force and we found the tensile force. Now to find the moment, how did you find the moment from the compressive force in working stress method?
So that compressive force into distance from upward, D minus.
How much was that?
What, sir?
How much was that distance, that lever arm?
So D minus KD by 3.
D minus KD by 3. Because triangle KD by 3 is the centroid, so you were able to find it easily. Here it's not a triangle, so you will have to sit and find out where the centroid of this whole shape is. And if you do it, you will find out that that centroid lies at 0.416 XU. Here it's shown as 0.42, but anyway, it's given as 0.416 XU is the distance from here to here. So therefore, find the compressive force multiplied by, here it will be D minus what now? It will be D minus, it's not shown here itself anyway. It will be D minus 0.416 XU. That will become the lever arm. Here to here is D, here to here is 0.416 XU. So subtract them, you get lever arm. Then just multiply this by that, you get, here the term becomes different. There you said allowable moment. Working stress method, you use the word allowable moment. When you use limit state method, you say ultimate moment of resistance. Okay, so U and R, it becomes MUR. So in an exam itself, if somebody is asking you, find they need not specify use the working stress method or use the limit state method. Based on what is asked itself, you can be able to guess. If they ask, find the ultimate moment of resistance, you should know you should use limit state method. If they say find allowable moment, you should know that you have to use working stress method. Okay. So based on the words itself, you should be able to guess what to use. Okay. So in case, so one thing is initially we do not know what is XU. We may need to find what is XU. without knowing XU, you cannot actually use this formula itself. So how to find XU? So here you have no other option. You're going to make an assumption. You're going to assume that your beam is under reinforced. Okay. So this is compressive force. Tensile force is given by stress in steel times area in steel, which is FST into AST. Now, if the beam is under reinforced, you know that steel is going to fail. Okay. So therefore, instead of FST, you can use 0.87 Fy itself, meaning the actual maximum stress which the steel can be allowed to reach. Okay. So 0.87 Fy. So you can just assume that the beam is under reinforced and say that the stress in steel is 0.87 Fy, and then you can just use the equilibrium condition, compression equals tension, and say XU is given by 0.87 Fy AST divided by 0.362 FCKB. Okay, so this is, you will just find this, and you will find this XU and compare it with what you got XU max. And if you find that yes, whatever you found XU based on this formula, if it is coming lesser than this XU max, then you know the assumption is right and the beam is under reinforced, and you can just proceed and do the whole thing, whatever is mentioned above. The alternate cases, and if that is the case, if it is under reinforced, you can either use 0.362 FCKB into D minus 0.416 XU. This is based on the compressive force, or you can also base it on the tensile force, which is 0.87 Fy AC times D minus 0.416 XU. And if your beam is under reinforced, whether you use this formula or whether you use the compression force formula, you will get the same moment. Okay. Better to use this for under reinforced beam because you know that certainly the steel has yielded. Now the second problem happens is, if you find out that, see here you do this this XU formula, you find out a value of XU, you compare it with XU max, and this time you find that XU max is actually XU is actually greater than XU max. So if XU is greater than XU max, what does it mean? What does it tell about the beam if XU is greater than XU max?
Over reinforced.
It is over reinforced. So if it is over reinforced, you have an issue. The issue is, if it is over reinforced, you cannot say that FST is 0.87 Fy. FST remains unknown if section is over reinforced. So the first thing that you will have to do if you get an over reinforced cases, you have to first of all find out what is FST. Okay. So if over reinforced, this is a mistake. This should be greater than symbol. Sorry, there's a mistake here. If over reinforced, which means XU is greater than XU max, then FST is not equal to 0.87 Fy, and the equation shown in the previous slide for XU cannot be used. Okay, cannot be used in the sense initially you will use it to find out XU, but once you determine that XU is greater than XU max, you cannot use that XU which you found. You have to correct it. So then the stresses in steel and XU need to be found through an iterative process. So it's a very simple process. What you will do is, you will first assume XU is whatever XU you calculated here by the formula, whatever you calculate plus XU max which is there. You take the average mean of it and say that is your trial XU. Then you use similar triangles. So this is 0.0035 and this is D, this is XU. So based on this similar triangles, you know that the strain in concrete is 0.0035. So you will find out what is this, the strain in steel. So once you know the strain in steel, you have a relation between stress in steel and strain in the steel. If it's mild steel, it is very easy. It's a straight line. If it is 415 or Fe 500 grade, then it is parabolic. So for our convenience, we have a table which we can use. Okay, depending on what is the strain you have found in the steel, you can just relate it with what would be the stress in that case. Okay, so this stress in steel, once you find out the strain, it may be calculated by using table A of, there's a design aid book called SP16 which you will be using, and I'll tell more about it later when we come to it. So there's a table in it which tells you these details. What is the relation between stress and strain in steel for these two different grades? Okay, so you'll find out FST based on that. So once you find out FST, you go back to this equation. You use that value of FST here and find out what is XU. Okay, you find out what is XU. Then once you find out XU, so you recalculate XU using the same formula, except you will use the FST which you calculated over here. Okay, and you will recalculate what is XU. So you will compare this XU with the XU which you had first. See if the difference is very small, is it converged? If the difference is more, repeat the process. If the difference is less, you assume that this is the final XU and this is the final FST in steel. And then based on that, you will proceed to do the rest of the problem. So once XU and FST are found, you can use, can find what using? Okay, you can find the ultimate moment of resistance using the equation either in point number 2 or point number 4. Either you can use this equation, except that instead of 0.87 Fy, you will have FST. So with that change, you can use this equation, or you can just use this equation because XU is known. So this is the process to find out for an over-reinforced beam. So design is the opposite of this. Probably the process of design probably we'll see in tomorrow's class, or maybe if possible we'll do some problems in this. Okay, so with this I'll stop. If you have a couple of minutes, just hold on one second. I'll unshare this. Okay, are you seeing my course plan?
Yes, sir.
Okay, this is last year's actually, but I am going to use more or less the same course plan. Okay, this last year I'll change it to 2021 now. And there's some small changes in your I think the columns. Yeah, okay, in this syllabus itself, I'll be not doing a few things. Okay, one thing is I'm not going to cover this flat slabs and staircases. Reason being, I started 2 weeks late, so we will not have time to cover it. Okay, no other reason. So flat slab is, it can be ignored from a BTech point of view. It can be ignored. Staircase design, you're going to do it as an assignment. It is, once you know slab design, staircase design is, it's just a direct application. There's nothing new to teach in it except types of staircase and how to take tread rise and those things. Okay, other than that, there's nothing else new, so I will not teach it. So other than that, everything else I will be teaching. Combined footing will be only, combined footing also I will not take. I'll just tell the principle, you will not get a problem from it. So this is one thing. Other thing is, you know, all these are just we are right now, where are we? We are here. Okay, we are it actually shows like we are in week 3, but we are only in week 2. I speeded up a bit because of the we started late. So right now we are here, then we have everything else to do. And also this was a 4-credit course previously, now it's 3 credit. Okay, the one of the things will be you will have quizzes every so often, which counts for about instead of 30, I'll be counting it for 20 marks. Okay, it will be for 20 marks and not 6 quizzes. There will be a total of 4 quizzes. It will be in Teams itself, objective type, and maybe 10 to 15 minutes each. You will just answer them and submit it, and the grades will come. So total 4 quizzes, not 6, and weightage 20. Then you will have assignments, staircases, slender columns, and combined footings. Okay, you will read by yourself and you will solve the problems. Okay, that will be assignment. You can submit it at the end. It will count for about another 20 marks. Okay, so this will be 20. This will be 20. Mid semester will be 30. Final assessment will be 30. Mid semester 30 marks, but I'll be giving 1.5 hours only, because the problems will be like that. You don't need 2 hours. Okay, just because it's 30 marks does not mean I'm going to set it for writing it, like writing for 2 hours. I'll set it such that it can be answered in 1.5 hours. Okay, marks alone I'll give more marks, 30 marks. Final assessment will be usual, as how it always happens, 2 hours, 30 marks. And mid semester you will have mostly till design for torsion. So this is till what you will have your mid semester. Okay, so this is the course plan. Of course, compensation and all will be given only for genuine reasons. If you miss quizzes, fail to submit within time, or do things like what you did last time and all, no, it will not be permitted. Adhere to the guidelines, adhere to the deadlines. And this is the assessment methodology. 20 marks, 4 quizzes, 20 marks, about 3 assignments studied by yourself. Mid semester 30 marks, final assessment 30 marks. So is this agreeable?
Yes.
Okay. And mostly regarding your course, what we are deciding is, I'll be taking all the classes for both the sections. Okay. And the other faculty number 2, whoever comes, he will be coordinating with me and conducting all the assignments and all those things. Okay. So class, as far as it's concerned, it can remain like this. It can remain one single teams itself. And I'll just be taking the classes, doing your tutorials, like solving the problems, teaching you and all those things. Evaluation, assessment and all those things will be taken care by the other faculty. Okay, this is what is being decided. Okay, fine. I think you also have to leave. So I'll just end the meeting. We'll meet tomorrow.
Thank you, sir.
Okay, thank you.